I'm going to solve some problems on optical interference, but before that, let me first talk about some interference basics, basic ideas on interference. So suppose if you have one source, so it produces circular waves, right, and that is spread out. Just like if you have a vibrator and if you use a ripple tank, shallow water, right, you can generate the ripple of waves that spread out, right? And this is the wavelength is the peak to peak distance, right? So these solid circles represent the crest, and the dotted circles say represents the trough, right? And this is the top view. Actually, it sends out a ripple of wave, but that's not particularly interesting. But if you have two sources, right, two identical sources in phase, for example, right, then you will see an interesting pattern, and those pattern are because of interference of wave, because they suppose they initially they start out with the same phase, right? They start out with same phase, but since these two waves, right, generated by these two sources have to travel different distances, right? um, they may meet out of phase, or they may meet in phase at a certain distance, right? If they superpose in phase, right, then at that point you will get constructive interference. So for example, solid circle meets with solid circle, these, right? These are the points with the constructive interference. However, if the crest meet with trough, so for example, this right here, here, then they meet out of phase, right? So that means these are the points for destructive interference, right? And then you will see this interesting pattern, and then you will see an interesting interference pattern with constructive and destructive interference. And if it is in optical interference, you need a double slit, right? Two narrow slits, two narrow holes separated by narrow distance. And then if this double slit is illuminated with light waves, right, or laser light, then on the you put a screen something somewhere here, and then you will see a bright and dark fringes, right, due to constructive and destructive interference respectively. But the main idea is, as the two waves, right, they travel out with same phase, but as they travel this different distance, they have to travel different distance. This path difference, brings the phase difference, right? And what's the relationship between path difference and phase difference? Right? This is the relationship. Since lambda is a full cycle, lambda will bring 2 pi phase shift. In general, the phase difference between two waves is 2 pi over lambda times the path difference. That's how you calculate, you know. And so using this idea, so in terms of path difference, so this is, let's say phi is the phase shift or phase difference between two waves reaching at any point, is 2 pi over lambda, right? And path difference, let's call delta L. So in terms of delta L, so if delta L is m times lambda, right? If the path difference is integer whole number of lambda, right, m can go from 0, 1, 2, 3. Then if you put that here, then they will meet in phase, right? In phase. That means in terms of phase shift, phase difference, it is 0, 2 pi, 4 pi, 6 pi, even number of pi, right? And they meet like this, right? These two waves at that point meet in phase, right? And they produce a constructive interference, bright light, right? So, however, if the path difference is odd half multiple of lambda, right, like this, right, m still goes from 0, 1, 2, 3, right here, odd half multiple of lambda, then it brings the phase shift of this pi, 3 pi, 5 pi, 7 pi, odd multiple of pi. Then the two waves will meet like this, right? Two waves will meet like that, and that produces nothing. And this is called destructive interference. Okay, so this is the basic idea of any interference, right? And we're going to use this in optical interference. So these are some interference, basic problems. Not necessarily optical interference. These are interference in electromagnetic waves. So it says coherent sources A and B, right, emit electromagnetic waves with wavelength 2 centimeter. Point P is 4.86 meter from A and 5.2 from B. What is the phase difference between at point P between two waves arriving here? So this is something like that. So if you have two sources, right? Two coherent source. Coherent source means they emit waves with same frequency, same speed, and have a constant phase shift, phase difference. So it says point P is right here somewhere, right? And these two light waves, these two electromagnetic waves, right, reach here, and they have a path difference. Say L1 is 4.86 meter, and L2 is slightly longer path, is 5.24 meter, right? These are and you can calculate the path difference, right? So it says, what is the phase shift, phase difference between these two waves arriving at? So first you need the path difference, right? Delta L we call path difference, because once you have path difference, then you can calculate the phase shift, right? So it's 5.24 minus 4.86, pretty simple, and that's going to be 0.38 meters, and the lambda, the wavelength of this electromagnetic wave, is given 2 centimeter, right, in meter. And then what is the, it says the phase difference between these two waves, and this is the relation, 2 pi over lambda times the path difference. So 2 pi over lambda is 2 centimeter times path difference 0.38. That's it, and this will be in radians because it has pi here. So the phase shift, phase difference between these two electromagnetic waves reaching here is is given by 119 radians. This is in radians. Okay. So that's it. This is the main formula. Okay, next problem. Similarly, so now back to optical interference, right? Coherent light with wavelength 500 nanometer passes through a narrow slit separated by 0.34 millimeter at a distance large compared to the sun. What is the phase difference in radiance between the light two slits at an angle 23 degree from the center line? So what it is saying is you have a double slit, right? Now, because in order to see the optical interference, you need double slit, right? So then you shine a laser light or any light waves, right? And this is called double slit separation D. D is the slit separation, right? And on the screen, right, this is the center line. On the screen, you view the interference pattern. This is the screen, and the condition is we consider L is much bigger than D, right? In all this approximation. So then you shine a laser light with 500 nanometer light, right? And this is D is given 0.34 millimeter, and it's acting now. You at any point, let's say point P, which is at 23-degree angle, right? 23-degree angle. What is the again? What is the phase shift? What is the phase difference between the two light waves? Just like this problem, right? Reaching here, right? And one more thing is in double slit in optical interference, the phase difference, right? If this is L is much bigger than D, the path difference between these two light waves reaching here is given by this extra-piece. Because if L is much greater than D, then this you can consider approximately, you can consider these two light waves are arriving here in parallel, right? If this is much bigger than that, and this is given, this is the your path difference, which is given by d sine theta. You can just do trigonometry. The path difference in double slit is 2d sine theta. That's it. So delta L is d sine theta, which is the path difference, is, and d is 0.34 millimeter. Millimeter needs to be in meter, and sine of this particular point is at 23 degree. Right? So first find the path difference between the two light waves reaching there, and once you calculate that, 1.33 10 to the power negative 4 meter. That's the path difference between these two light waves reaching here. Then you can find the phase shift easily. 2 pi over lambda times the path difference, right? And 2 pi over the wavelength of the light used is 500 nanometer. Nano means -9. And delta L is 1.33 10 to the power -4. And this is again will be in radians. We get it as pi, right? 1670 radians is the answer. That's the phase difference between the two light waves arriving here. So here's the next question. It says two narrow slits, that means double slit, are illuminated by light with wavelength lambda. The slits are spaced 20 wavelengths apart, right? That means you have a double slit, right? Two narrow slits, and this is we call D, and it says D is 20 lambda. It gives you the slit separation in terms of lambda. What is the angle in radians between the central maxima and the second bright fringe? So on the screen further away, right, the central will be obviously bright fringes, and so it's acting. This is the central fringe, and this is the first bright fringe, and this is the second bright fringe. They are equally spaced. It's acting. What is the angle between the central line and the second bright fringe? This angle, right? So since you are given D, and again the condition is right, L has to be much bigger than D. Then if L is much bigger than D, then you can use this, since this is the second bright, right? So you can use the condition for constructive interference. The path difference, right, delta L is D sine theta in double slit, right? Has to be m times lambda in order to produce the constructive interference bright fringes, right? And m is 2 because it's acting the angle for the second bright fringe from the central line. So m is 2, so then you find out theta. That's it. Sine theta is 2 lambda over D. So 2 lambda is not directly given, but D is in terms of lambda 20 lambda, right? So lambda will cancel 1 over 10. So theta is inverse sine 1 over 10, and that's going to be, if you do that, 5.74 degree. Okay. So second question is now same, just continuation between the central maxima third dark fringe, right? Same double slit, right? So, but you're now measuring the angle for the third dark. So the central will be bright, right? And let me just first draw the bright fringes. So this is the first dark, right? This is the first dark. Second dark, and this is the third dark. And it's acting, what's the angle from the central line, right, to the third dark? Third dark, right here. That's the, and this is the same double slit, right? D is 20 lambda. And now we're just, since we are measuring the angle of the third dark, right? Third dark fringes from the central line, we're going to use the dark fringe condition, that means destructive condition. So destructive condition, destructive interference condition is, right, delta L, path difference between two light waves, has to follow this relationship. D sine theta, it has to be m plus 1/2 lambda. But third dark, right, from this relation, right, first dark is 1/2 lambda, second dark is 1.5 lambda, third dark is 2.5 lambda. So third dark occurs at m is equal to 2, right? Because 0 corresponds to first dark, so it's always less than 1 for dark fringes. That's it. So then d sine theta, if you put 2, right, 2.5 times, it has to satisfy this condition, 2.5 lambda, in order to see the third dark fringe, right? And then you find the theta. So sine theta will be 2.5 lambda divided by d is 20 lambda, right? And 2.5 over 20, and then theta is, if you do that, 7.2 degree. Okay, so the third dark would be at 7.2 degree. Okay. So that's the, and let's do the last one on this. It's just again, this is just a continuation of the same problem, right? And the next question is, calculate the lateral distance between the third dark fringe from the central fringe in millimeter if the distance from the slit. Now it's asking same question, right? For the same question, now you're given this distance, the distance between the double slit and the screen is half a meter. If that's the distance, then what is the lateral distance? So it's just asking right down. So let's say this is the third dark. It's asking this distance, this lateral distance, y. And since we already know this angle, right, 7.2 degree from the part B, then you can easily find this lateral distance, right? How far is this third dark from the center, right? Central bright fringe. You can just use the trigonometry now, right? So I'm just going to take tan theta. Tan theta is y over L. So your y is L tan theta. L is half a meter and tan of 7.2 degree, right? The third dark will be at so first you will get in meters and then convert back to millimeters because it wants in millimeter. So the third dark will be at 63.2 millimeter from the center bright. So here's the next question. So here's you use helium neon laser through double slit, and this is the slit separation, and find that the third bright line, right, on the screen, third bright fringe on the screen is from at 10.95 degree relative to the incident beam, right? The slit to the screen distance is 80 centimeter. What is the wavelength of light? So same thing again. You have a double slit, right? And this is the screen, and this is the central line, right? Central bright, and the third bright, right? This is the third bright, which is corresponds to M is 1, right? Is at 10.95 degree, right? And the distance between the double slit and the screen is 80 centimeter, right? And this slit separation is 0.1 millimeter, right? And based on this information, now it's asking what is the wavelength of the light used in this experiment. So third bright is at 10. So again, so you're given the third bright position, right? So then you have to use the constructive interference condition. Constructive interference condition is d sine theta is m lambda. So third bright means m is equal to 3, right? M is 3. So then lambda is going to be d sine theta divided by 3. That's it. So d is 0.1 millimeter needs to be in meter, and sine of this is at 10.95 degree divided by 3, and that's your wavelength of the light used in this experiment. So 0.1 negative 3 times sine of 10.95 degree, right, divided by 3, and that's going to be so this is going to be I'm off by 0.01 millimeter. So this is 0.01. So 633 nanometer in terms of nanometer, because the wavelength of the light is usually expression nanometer. Okay. So next question. What is the position of the fourth dark measured from the sun? So for the same question, what is the fourth dark, right? So then dark condition is what? Destructive interference condition is, right? D sine theta is m plus half lambda for destructive interference, right? So fourth dark occurs at m is equal to 3. It's less than 1, remember, because first dark occurs at 0, m is equal to 0. That's right, fourth dark. So that's it. So the position of the fourth dark, right? So position of the fourth dark, first we're going to find the angular position, then find the lateral position, right? It's just action. So this is the fourth dark, right? Let's say fourth dark is action. What is this distance? What is this distance from the center? So first we have to find the angle, right? Then you can find this angle for fourth dark is sine theta is, now this becomes 3.5 times lambda divided by d. So everything is good. 3.5 lambda is, now we have already found lambda from first part, 633 nanometer, nano, right? Divided by d is 0.01 millimeter. So that's your theta. So find theta, right? Sine inverse, whatever you get, and 3.5, 633 nano divided 0.01 and inverse sine. So it's going to be 12.8 degree, right? And then since this double slit to screen distance is given, so tan, you can just take the tan of theta is L over y over L. So the lateral distance, this fourth arc is at that distance from the center, is L tan theta. L is given 80 centimeter, means 0.8, right? This is 80 centimeter. And tan of 12.8 degree, and that's 0.8 times tan of 8. So it's 0.182 meters, right? And you can convert back to centimeter or millimeter if you want. So 18.2 centimeter, right? Okay, that's the second part. The third part, last part, is now calculate the intensity of the spot at 20 centimeter distance from the central bright spot, right? In terms of I naught. I naught is the intensity of. Now it's actually the intensity question. Intensity of. So same double slit, right? So now it's acting. So this is the central bright, right? It's acting at. What is the intensity of the light at this particular point? Let's say point P, right? Which is at 20 centimeter distance from the central bright, right? So that's the. So first, to find the intensity, here's the intensity formula we have, right? For double slit intensity. I is I naught cos square phi over 2, where phi is the phase shift between, phase difference between the two light waves, right, reaching at that particular point from the double slit, right? Phi is the phase difference between these two light waves from the double slit. It's so then to find that, first, again, the path difference is d sine theta, right? And first you have to find this angle, this point particular angle is what, so right, so since this theta, you can do tan theta is 20 centimeter divided by this is 80 centimeter, right? This is 80 centimeter. It's the same experiment. So first find that particular point, the angular separation, right? So inverse tan 20 divided by 80. So this 14 degree, right? This particular point is at 14 degree. Now from here you can find the path difference, d sine theta, right? So then the phase difference between the two light waves reaching here will have 2 pi over lambda times the path difference, right? But path difference is d sine theta in double slit. Path difference is d sine theta. So, and this will be in radians, right? So find that out. So d is the same d, 0.01 -3 times sine of now this 14 degree and times 2 pi divided by lambda is the wavelength of like 633 nano. So this is 24 radians. 24. This is radians, right? And you can convert back to degrees if you want, or change your calculator into radians. So this is 1376 degrees, right? Now finally, then you can now go back and put it here is cos square 1376 over 2, and that's your intensity, right? Cos of that degree and square. So 0.72 I naught. So the intensity of light, right here at this particular point, which is 20 centimeters from the center, is 0.72 I naught, where I naught is the intensity right here, intensity which is the brightest, right? Intensity of the light at the bright fringe at the center. So here's the next question. So you're given the interference fringe pattern, right? When light is illuminated through a double slit, you will see this interference pattern on the screen, right? And these are bright and dark fringes, right, due to interference. And the first question is actually, what is the wavelength of the light used in this experiment, right? And you can first write down the condition. This is the condition for constructive interference, so you can find out the lambda, but you don't know what is the theta. Theta is the angle, the angular separation of one particular fringe, bright fringe, from the center line, right? But since in all these, actually all the angles will be small, right? All the angles will be small. This is the L is the slit to screen distance, which is given, and this is, let's say, this is the Y of M, this distance Y of M, right? This is the bright fringe, right? Of any order bright fringe. It could be first order, second, right, third bright fringe, any order. But here tan theta is Y if you just use the trigonometry. But for a small angle approximation says if the angles are small, tan theta is approximately equal to sine theta, right? So then you can just use lambda is d over m. Sine theta now can be written as tan theta, right? Tan theta is ym over L, right? And then just pick one of the bright fringe. So if you choose, second bright fringe, right? M is going to be 2. So because the distance is no ym, now y2 is 1 centimeter exactly. See, this is 6, this is 7, so 1 centimeter, right? So if you choose a second bright fringe, your y2, this distance is actually 2 centimeters. So d is given is 140 micron. Y2, we're measuring second bright fringe, so 1 centimeter. M is 2, right? Because we picked second bright. You could choose first bright fringe, or you can pick any bright fringe you want. And L is 1.1, and that's your answer. So 140 micron, 1 centimeter divided by 2 in 1.1. So 636 nanometer in terms of nanometer, right? Or since these are small angles, right, you can, if you remember, you can directly use the formula. This beta is the fringe shift formula, lambda L over D. You can directly use this and calculate, you can calculate the wavelength of the given light, right? So beta is the fringe separation. That means the distance between any two brights, which you can get from here. Okay, now next question is, what happens to the pattern, the fringe pattern shown in the photograph, right? If the laser is replaced by, if the given laser is replaced by blue laser. So we know that blue laser, right? Blue laser has a wavelength, shorter wavelength compared to this one, because blue wavelength has about 450 nanometer, which is shorter than that. So if you use, this is a red, right? This from the spectrum. Blue laser has shorter wavelength compared to red. So if you use shorter wavelength laser, right, light, then this, what happened to the fringe shift? I mean, this fringe, do they increase or decrease? So then from this fringe shift, right, fringe separation formula lambda L over D, then you can directly see the relationship, right? For the given L and D, which are constant, so beta is proportional to the lambda, right? So if you use if you use the blue laser, which is shorter wavelength, then beta will also decrease because they are proportional, right? So you will then, if you use the blue laser, blue light, then you will have the interference pattern whose fringe separation will be smaller than before. That's the answer. Okay, now next, what happens to the fringe width, right, which is beta, right, in our symbol, if you use a double slit with larger slit separation? Now, use the same laser for the given, so again, back to the same formula, right? For the given wavelength and L, right, if these are constant, beta is now inversely proportional to D. So now if you use the D with larger slit separation compared to the B, beta will have smaller separation. Fringe separation will decrease. Now, next question. What is the phase shift between the two light arriving at 8.3 centimeter as shown in the diagram below? So 8.3 means where? 8.3 is somewhere 1, 2, 3, right? 8.3. So 8.3 is at what distance from the center? Let's call y, right? This distance is 8.3 minus. So this is, and from the side view, this is like this. So we're finding the phase difference between the two light waves arriving here, right? At this point P, let's say point P. This is 8.3 centimeter, but center bright. Let's say this is center bright, right? Center bright is at 6 centimeter, right, from the given picture. And so that's why this, let's say this distance, lateral distance is 2.3 centimeter, right? And then first you're going to need this angle, right, from the center line. So theta is going to be, because this is given, this is 1.1 meter, right, is inverse tan. So 2.3 centimeter means in meter this 1.1. It's going to be very small angle, we know, right? So let's find that out. So this angle is inverse tan 2.3 divided by 1.1, and it's 1.2 degree, right? Then once you have that, then the path difference between these two light waves reaching here is d sine theta, right? And then the phase difference between the two light waves reaching here will have 2 pi over lambda times the path difference, right? 2 pi over lambda. Path difference is d sine theta. That's it. That's the phase shift. Phase difference between two light waves reaching at this particular point. 8.3, somewhere here. So 2 pi over lambda is the wavelength of light used, which we found from part A, 636 nanometer. And D is, the slit separation is 140 micron, right? And sine of theta is 1.2 degree, right? And that's it. So 140 micron times sine of 1.2 degree times 2 pi divided by 636 nano, and it's 28.9, so about 29 degree, 29 radians is the answer. So that means the phase difference between these two light waves reaching at 8.3 centimeter position right here, right, the two light waves reaching here, will have a phase difference of 29 radians. So here's the next problem, and this problem is on diffraction grating. Diffraction grating is just a multi-slit plate. We shine light into a diffraction grating, right, that has 550 lines per millimeter. And then what's the distance between the two lines? So first question is, so first of all, what is diffraction grating? Diffraction grating is a multi-slit, right? It has many lines like this, many lines ruled or fabricated per millimeter. So it says 1 millimeter has 550 lines, right? And this is the diffraction grating. So this is the grating plate, right? And it's asking first question, what is the distance between two lines? So then you are given 1 millimeter has 550 lines, but what is the distance between these two lines, which is D, which is the slit separation actually, right? We call slit separation, which is the distance between just two lines. That's the first question. So then, since 1 millimeter has 550 lines, what would be the, so D is, you can just directly use this formula, W over N. W is the 1 millimeter, right? Millimeter needs to be in meter. And 1 millimeter has how many lines? 550 lines. That's it. So that's, and its answer 1.82 10 to the power negative 6 meter. Okay, 1.82 micron. So see, you have microscopic lines, right? The lines in this diffraction grating you cannot see. It's in because it's micrometer range, right? So that's the first question. Second question is, what are the angular and lateral position first and second orders of diffraction maxima, right, for blue light? So now, if you, so this is the multi-slit, this is the diffraction grating, right? And on the screen, you, if you shine a laser light or light in it, that you will see these well separated dots on either side. These dots, right? Like this. This is M is equal to 0, M is 1, first order, M is 2 is second order bright, right? First, what is the angles, right? And also the actual distance from the center. So these angles, theta 1, theta 2. And so we just use the condition for bright interference, right? Constructive interference. These bright fringes will appear because the path difference between the two light waves reaching here, right? All the light from all these slits will follow this. D sine theta is m lambda. So theta 1 is then inverse sine m is 1, right? Lambda over d. That's the angular separation of the first bright fringe. If you do that, because lambda is, it says blue light 450 nano, and d is from part 1 1.82 10 to the power negative 6. So this is now 14.3 dB. And the second bright fringe, right? The second bright spot will be at similarly now m is 2, right? M is 2, so 2 lambda over d. Do the same thing, and it's going to be 29.6 dB. Now once you have these angles, right, this distance is given to you. This distance is, let's say, one. I should give you this distance, but I'm just assuming this is 1 meter, right? This will be given. So then what is this lateral distance, actual distance from the center order, center bright fringe? So y1, this is your y2, right? So y1 will be, just use the trigonometry, L tan theta 1. 1 tan theta 1 is 14.3 dB. And that's going to be 0.255 meter. What is the second bright fringe? So second bright fringe will be at this distance, theta 2. 1 tan of 29.6 degree, and this is going to be 0.568 meter. Okay. So that's part B. Part C is now, what is the maximum number of bright fringes that you will be absorbed? It will be absorbed on the screen, right? So how many number of dots you can see is limited by the wavelength of the light you used and the number of lines ruled per millimeter on the given diffraction grating element. So let's find out. So d sine theta is m lambda. So let's first find out the maximum possible value of m, right? Which is the number of dots on each side, right? M represents the number of bright dots on each side. Is then d sine theta divided by lambda. So what is the max? So we are finding the maximum possible. So then d is fixed, lambda is fixed. So then the maximum possible value of sine function is 1, right? So the m max is d over lambda. So d is given 1.82 10 to the power negative 6 from part A. Lambda is 450 blue laser. So then m max, the maximum number of dots on each side is then, right, you can do that. So L, the m is 4. But this is just the one side, right? So the total number of dots, then total number of dots seen on the screen is twice m plus 1, right? 1 means 1 represents the central dot, because central dot is going to be bright as well, right? So because you'll have symmetrical order, right, of diffraction, this symmetrical order of dots, right, on each side, like this, right? This is m is 0, let's say, right? So you have 1 2 3 4 on one side, 1 2 3 4 on side. So you will have, in this case, so 9, total of 9 dots. You will see total of 9 dots on the screen, right? And this is how you can find.